из университета Луисвилля, а перед этим у него был долгий-долгий путь, когда он работал в нескольких ведущих лабораториях американских, и потом уже самостоятельно, знаете, где он работал в университете Луисвилля, он уже примерно лет 15, сейчас он там полный профессор, и он у него лаборатория, которая занимается вещами, о которых он будет говорить сегодня, завтра, послезавтра. И примерно, наверное, в течение 3 лет, через 15 наших магистров и аспирантов были на стажировке у него и другого нашего коллеги, профессора Гамини Суманасекера. И ребята, которые мы были 2-3 месяца. И я думаю, что было очень полезно всем, кто с ним работал. Эти месяцы были очень полезны. И мы рассчитываем продолжать эту программу сотрудничества, кроме научной программы. Общем, мы программу стажировок надеемся осуществлять, и этим летом мы надеемся, что будет день представительства новых людей туда, и это может будет несколько побед. Слушайте, задавайте вопросы, перебивайте, останавливайте, пытайтесь выяснить все, что вы хотите, не стесняйтесь. Тоже замечание, связано с ним, 2 недели назад был профессор Кентукки, его читал замечательную лекцию, а потом вместе с ним мы сходили на Перми, и его ведущая спросила, чем отличаются наши студенты, наша аудитория в Израильском университете. Он сказал, что очень отличается. И одно из отличий, что все очень страшно молчаливы. Никто не спрашивает, что так нужны, боятся показать, что чего-то не знают. Это грубо. Сразу же останавливайте. Потому что у вас есть какие-то проблемы с английским, мы договорились. Наш официальный переводчик. Совсем Миша.
Меня зовут Базе, я сегодня говорю,
у него хороший английский, а по терминам, Алексей полностью стажировка, например, терминология, если вы решите проблемы, разговаривали про них, решили будет вам прописывать сегодня переводчик, поэтому через них можете обращаться к профессору, можете спросить, но все скажут, то есть просто разговор с ним, просто беседа. Мы пришли, собрались, узнать, чем заниматься.
Thank you very much, Victor. Guys, nice to be here. So I was here. I think Victor mentioned, like, if you have any questions, please stop me. If you don't understand or if I go fast, please stop me and ask some questions. So today I'm going to talk about recent advances in electrochemical energy storage materials.
Последние исследования по электрохимическим.
А вообще вы нужно переводить все, да? Либо то, что вы видите, это понятно. Ты включайся, когда чувствуешь. Давайте ему знать по сигналам или...
Когда вам нужно будет перевести?
Значит, это очень долго, если все
Okay. Yeah. So why is electrochemical energy, especially energy storage, why it is so important? Yeah. So if you look at energy storage, we know we need a lot of energy storage for transportation purpose. So for example, for hybrid electric vehicles, so we need to have some energy storage needs here. So then also we need a lot of energy storage for renewable energies like wind or solar energies. So when you generate this electricity, we need to store them. So then also, so consumer electronics, your laptops, your cell phones, we need good storage medium, right? So finally, also some energy efficient buildings. That's okay. Yeah. So we need smart buildings so where you can have efficient energy storage here. So then finally the left here. So we have very large scale energy storage. So when you want to connect with the national grid, it's a more like regulated energy delivery. So when you store this energy, you should be able to deliver to the national grid. From the national grid, it will be supplied to the consumers and whatever is. So this is mostly the transportation I was talking about. So transportation, we have this hybrid electric vehicles or plug-in hybrid electric vehicles and electric vehicles. They all need good batteries ready to store your energy. Then if you go to heavy duty hybrids, the very large trucks, you need storage needs. So then, especially in the aviation, like airplanes. Recently, there was a fire in an airplane because lithium-ion batteries, they exploded. So then, this is the renewable I was talking about, the wind and solar. So when you have this large energy generation, so you don't use it immediately, right? You make energy, but you don't use it, and what you do? You don't waste it, you just store it. So then you can either give it to the national grid or just store in your large storage grid. So finally, the grid stabilization. So that is, so if you have this network energy system, you can power large cities like Permski, so you can provide that energy by through networking, or even from large plants you can provide that energy to your transmission lines. Okay. Yeah.
Потому что применение записания энергии, то есть это нужно для машин гибридных, гибридных машин, которые могут работать полностью на электричестве, которые могут работать одновременно, то есть у них идет использование топлива и электричества, и полностью на электричестве, никаких топлива не используется. Там нужны достаточно большие емкости энергии. На грузовиках, потому что они весят большие расстояния, используют большие мощности, и нужны большие емкости энергии. Авиация, конечно, большие литий-ионные батареи, и нужны новые какие-то емкости, которые могли бы использоваться в авиации. Также, когда вы используете хранения, мельницы и солнечные батареи, вы же не используете сразу эту энергию, вы ее запасаете. И если это достаточно большие плантации мельниц или солнечных батарей, вам нужно, чтобы эта энергия скапливала большое количество. Также, вот он говорит, это электрическая сеть, которая по всей стране используется. Мы можем ее из тех мест, где эта энергия получается, места, где она может использоваться, например, в городах. То есть ее передавать с помощью таких проводов из мест, где она скапливается большое количество, и ее
So this is a hybrid maybe, yes. So here typically all this electricity is DC, right? Direct current. So if you want to use it here, these are still AC, alternating current, right? So then you need to convert from DC to AC using some inverters, or sometimes DC to DC with converters. That's all come here. Okay, so that's basic introduction. So now, when you talk about energy storage, battery is not the only alternative, right? So there are a lot of other storage techniques. For example, we have flywheel energy storage, compressed air energy storage, pumped hydropower, so that we all know. So there's some new techniques used based on superconducting magnets, supercapacitors. So, but today I am mostly going to talk about electrochemical storage, not any of these things there.
все-таки это не единственный способ записать энергию. Также есть устройство, где оборот обращается с некоторой частотой, и мы записаем энергию по обращению оборота, потом мы замедляем оборот, и у нас энергия является, которую мы используем где-то в наших сетях. Также на следующем слайде мы просто покажем, какие еще виды записания энергии есть. Но сегодня наша лекция о том, как записать электрохимические.
This is some. Yeah, so this is what I was talking about. Flywheels. Flywheel is basically you have a spinning wheel here. So then you store energy as rotational kinetic energy. So then you store that kinetic energy, then you can reuse later. So in hydropower, we all know, so we have water, so we just pump water and store as potential energy. So then you can reuse when you go. So this is another storage. So compressed air. So when you produce your energy, you use that energy to compress air underground. So this is ground. So this is underground. You can store energy by compressing air. So then when you want, you just take that energy to power your generator. So these are some of the standard energy storage systems. But I am not going to talk about these. I am going to talk about the electrochemical energy storage.
Вы мне рассказали об этих способах записания энергии. Первый это у нас вращается ионного рода. Чем быстрее вращается, вот у нас есть формула пропорциональной частоте в квадрате. Сколько у нас энергии запасается. Уменьшая частоту, энергия выделяется, мы ее используем. Также мы можем накачивать воду куда-то в хранилище, используя потенциальную энергию. А когда нам нужно, открывается срок, у нас туда начинает течь, там идет колесо, и следующее, это то же самое, как записать воду, только мы направление подаем воздух, и когда нам нужно, мы открываем клапан, у нас воздух идет, то же самое колесо и энергия является. Но сегодня мы поговорим об этом, мы поговорим об о нашей батарее, какие мы можем использовать.
Now, this is electrochemical systems we usually talk about. So this axis is power. So this is like what per kilogram. So power is more like you can think in a car. It's like the acceleration. How fast you can accelerate your car. So this axis is specific energy, that is what hour per kilogram. So this energy, this is power. So this you can think as how far you can drive your car. Okay? So this is how fast you can accelerate your car. This is how far you can go your car. So if you look at current status, you can see gasoline and hydrogen, they see pretty high energy storage, right? The energy is very high. That's why still we like gasoline. So hydrogen is very close to gasoline, but that technology is still not there. So a lot of research to use hydrogen for this energy storage, especially for vehicles. But if you look at batteries, so they have reasonably high energy density, but power is very small. Right? It's not good for acceleration. It's good for long distance. The flywheel sits here, little better than batteries. But capacitors, so they have very high power, but they don't have enough energy. So what we need is something, maybe push batteries and capacitors maybe to somewhere, maybe here. That will be good, right? So you have good energy and you have good power. It's impossible to get here, but if you can get somewhere here, that would be good enough. So there's a lot of research to push. We make what is called the hybrid. You can get battery electrode and capacitor electrode and make a hybrid. You can make it somewhere here. technology. So this is a hybrid, plug-in hybrid electric vehicles. So this is how you can store solar energy using battery pack to power your house. So these are another two important primary batteries. I don't know, you all are familiar with the pacemakers. So artificial pacemakers, right? We all have natural pacemakers in your heart, right? So if you take your heart in your right atrium, so we have some cells, they produce some pulses. That's the natural pacemakers. But if you have irregular heartbeats, so you have to put an artificial pacemaker. For that, you have to have some batteries. But those batteries you cannot recharge. Once you implant your device, it should last very long time. So at least 10 years before you use it. So long time ago, this is how the pacemaker battery pack was. They had like 10 batteries and 2 transistors. But nowadays, we have a very small device, only 1 battery, about thousands of transistors. So these are primary batteries, no recharging. But thing is, they only require microamperes to support your heart. So that means they can last very long time if you have enough capacity. Pacemaker. It's okay. So this is, I don't think this, I already explained these things later. So today my talk is going to be on these 3 batteries. I'm going to talk about what I have done in my lab to improve these lithium-ion battery electrodes. So we have very interesting new results on lithium-ion. Then we are doing some work on lithium-sulfur. And finally, supercapacitors. We use biomaterials to produce my supercapacitor electrodes. So that's because I'm from Louisville. So Louisville have a lot of distilleries around. So they make, after they brew alcohol, so the waste, we call it distilled dry grains. So they don't know what to do with that. So they don't have a way to dispose them. So now we get these grains and we activate it and make activated carbon. So they are very good for supercapacitor electrodes. It's all bio-based materials.
Интересно перевести. Понятно или нет?
Если честно, мне немножко...
Но в искусстве там очень много делают бурб, там знаменитое место для бурбана. Весь бурбан, который делается, это только на самом деле правильный бурбан, это Луисвилль. И у них, когда они когда готов, остается переработанное зерно. И это зерно очень сложно утилизировать, его очень-очень много. И они его отдают им, и это может быть использовано, эти колоссальные отходы для производства вот этих биологических сверхкапаситора. Капаситор, по-русски это конденсатор. Слово полетело. Все понятно.
So when you talk about batteries are not new, right? So we knew batteries even in like early 1600s. So Galvani, Gilbert, so they first introduced the first batteries, right? So now it has gone through a lot of developments. So then they developed nickel cadmium batteries. So then finally in 1991, Sony introduced the first lithium-ion battery. So that's the same technology we use even today with your laptops and your cell phones. So, but they have very small capacity. you have to charge your laptop every day, right? So that means it doesn't have enough capacity. We like to have some battery, maybe if you charge once, if it lasts for 1 week, I think that's a good battery. So that's a lot of interest of making very large capacity lithium-ion batteries. Not only for these things, especially for cars, automobile, so electric vehicles, or even plug-in hybrid vehicles. So I'll show later what we need for those things. So I think I showed this one last year also. But it's very important to understand this when you talk about the electrochemical potentials. I think probably chemistry people, they know this much better than physicists. So when you talk about the electrochemical potential, usually we use this standard hydrogen reaction as our zero electrochemical potential. So based on that one, we define positive, we call the more strongly oxidizing elements and also strongly reducing elements here. We can see like lithium is the most electronegative number here. So actually it's the more electron affinity here. So then fluorine has the highest positive potential because that's in the other element. That's why we are very interested in lithium for these batteries. It has the highest electrochemical potential and that is the lightest element, right? So hydrogen and helium are gases. So this is the very first metal, that's the lightest. Then also it has the highest potential. So that's why we like to have lithium in our batteries. But nowadays there are some interest on using like this is monovalent, only one electron, right? So lithium gives only one electron. But if you can have something that can give 2 electrons, so then your capacity should be increased, right? There are a lot of interest now, sodium batteries, even magnesium batteries. But lithium is still the benchmark for batteries. One last thing I want to give introduction. So what is the, when you have a battery, we know that there's a certain voltage, right? So we know 1.5 batteries, so 3 volts, 9 volt batteries. The cell voltage is coming from this simple equation, right? So this gives free energy, and if you have this Faraday constant, we know that is 96,500 coulombs per mole. So this is the number of moles. So from this equation we can calculate our what is called the open circuit voltage. So typically these voltages so come in like 1 volts to 3 volts. So like carbon has very small voltage like 1 volt, but if you go to some this oxide they will have like 3 volts, 4 volts. So but if you take a battery, you have two electrodes, right? You have anode and cathode. So then your cell voltage is given by the difference between the two electrochemical voltages. Okay.
Вы привыкли, что батарейки у нас электроид напряжение 1,5 вольта, 9 вольт и так далее. Откуда появляется эти волны? Появляется из строя электрохимических, которые через свой F это постоянная вода, она постоянна. R это количество моля участвующих реакций, G это то, что продолжено в нашем слайде. Вот. Но ведь движение появляется у нас из 2 электрона, такое движение складывается в этой форме,
What's it? This is electrochemical potential.
Электрохимический потенциал катода, электрохимический потенциал элитного потенциала это волны, вот у нас будет наши движения.
Yes.
Да, это у нас.
So later we talk more about this one. Okay, so now if you look at typical rechargeable batteries, so everybody knows this one, right? Lead-acid battery. This is what you have in your car. Car batteries, lead-acid. You have lead. Typically you have lead oxide. Then you have sulfuric acid. Right? That's the car battery. So that's actually not very high density or high power, but it's pretty good, right? So we still use these batteries for a long time now. So, but if you go to like nickel cadmium, nickel metal hydrides, they have much higher energy densities, but lithium ion is dominating charge. But actually if you use just lithium metal, that's higher than lithium ion, but you cannot use lithium metal, that's not safe, right? So it's very highly flammable. So that's why lithium ion batteries are very exciting. But it has some safe issues. That's why, because your electrolyte here, if this is a liquid, they can leak out. So for that reason, people are trying to use polymer electrolytes. So they are more like gel or solid state electrolyte. Then you don't have that leakage problem. So that can be safe. That's why it's a polymer lithium ion. So this is basically why I interested in lithium ion. That should be it. Okay, so this is another slide I want to emphasize. So like this is again power, like acceleration, this energy, like the range, how far you can go. Right? So you can see, if you consider these three hybrid, so this is the electric vehicle, this is plug-in electric vehicles, this is hybrid electric vehicles. So what is electric vehicle? That means no internal combustion engine, no gasoline. Everything is by battery. That means you need to have very high power or high energy battery. So you can see lithium ion battery cannot fulfill that requirement, right? So current lithium ion batteries are not good enough for electric vehicles. But it's good for plug-in electric vehicles and hybrid electric. What is hybrid electric vehicles? So that you can use both gasoline and battery same time. So that means you don't need to have very high battery, right? Because you get boost from the gasoline. But hybrid, plug-in hybrid means once you charge, you can just go by, if it is fully charged, you can just go by the battery. If it is not, then you can go to your petroleum, so your gasoline. So you can see electric vehicles requires because no the gasoline. So you need to have the best battery, but lithium cannot fulfill that. That's why we are talking about next one, some other, not lithium ion, something like lithium sulfur or some other technology.
Здесь? Да.
Okay.
Так. Здесь мы приводим графики мощности и записание энергии. Мы уже говорили об этих типах машин, то есть полностью использующие электрическую энергию без топлива, машины, которые могут использовать как батареи, так и топливо, причем они могут абсолютно спокойно обойтись без топлива, если у них полный заряд машины. И гибриды, которые используют одновременно и топливо, и батареи. Ну, на батареях они просто больше приедут. Как мы видим, литий-ионные батареи покрывают только первый гибрид. И до полного электрического автомобиля мы не можем дотянуться. Поэтому мы думаем о том, какими другими батареями можно заменить литий-ионы, например, литий-серный.
This is the internal combustion engine, so that has value. That's right. Yeah.
I see.
What's it? It's the internal combustion, the engine. Internal combustion.
Внутреннего сгорания. Без сгорания внутреннего давления.
Нет, двигатель внутреннего сгорания обычно, да. Нет, это обычный двигатель внутреннего сгорания, по-моему. Обычный мотор бензиновый, без всяких дополнительных. IC engine. Да. Ну, дизельный тоже, да.
Okay, so now let me quickly work on lithium-ion battery. How does the lithium-ion battery work? So you have your anode, and you have, so this is your anode, or we call the negative electrode. So this is the cathode or positive electrode. So typically when you charge means what? When you plug your battery into the outlet, right? Then you are charging. When charging, what happens is this lithium ion that coming from the electrolyte here. Electrolyte is typically this lithium phosphorus hexachloride in some organic like diethylene carbonate and ethylene carbonate. They are some organic. So that lithium ion is going inside these graphite layers. So that's why graphite is very nice structure, right? Lithium ion can nicely go inside. So when that happens, we say discharging. So now, what happens when I discharge? Discharge means I remove the air and just let it run. So then you are consuming your energy. Then discharging, what happens is that lithium ion comes out and go inside the cathode material. So that is the discharge. So important thing is when you charge, discharge, if you do this maybe 1,000 times, so things will change, right? Your electrodes can deteriorate, so it can go bad, your electrolyte can become bad, so then that's when you need to replace your battery, right? So to have a good battery, you should be able to charge and discharge at least maybe few 1,000 times, right? That's why good batteries. So also you need to have enough good charging time. So if it takes maybe 1 day to charge, it's not good, right? If you charge, you should be able to charge within short period of time. How long it takes? This one takes more than an hour, right, to charge your battery. So once you charge, it should stay long enough. It should not go down. So if I be charging, so I don't want like this. I want charge like that, right? But discharge, I don't want this one. I want discharge to be long, right? So then also this, how far you can, how many cycles you can do. If I can do this like several thousand, then it's a good battery. That's the whole idea. So if you take this graphite, unfortunately, graphite reaction is lithium react with carbon. So then it makes lithium or lithium Xc6. But for graphite, this X is 1. That means for 6 carbon atoms, you get only 1 lithium ion. So that's, when you calculate that one, your capacity is only 372 milliampere hours per. So this is the unit, typical battery unit is this milliampere hour per gram. So this is charge, right? So this is time, sorry, current times time. This is charge per gram. So this is not very big number. It's only 372. So that limits your battery capacity. But if you look at the cathode, that has even lower number. So that's why we are trying to make some battery that has much higher this value and also to have much better charging cycle. So that's some of the challenges. Anode conductivity is a problem. The graphite is a very good electrical conductor. If you use other materials, so they don't have enough conductivity. So then also this is very important. It's called the solid electrolyte interface. When you have this electrode, so this is in liquid. So it makes some kind of layer here. So we call the solid, that's coming from the solid, then the electrolyte and some kind of interface. So that's not good. So then once this forms lithium ions cannot go inside DC. So there are a lot of problem with this solid electrolyte interface formation. That's some of the challenges from the anode. Cathode always they have smaller capacity. So that's
И недостаток емкости чая он может сложиться с электроном. И это тоже одна из проблем, которую мы встречаем на зеленом электричестве. По подходу это маленькая емкость и недостаточно, иногда недостаточно безопасности ситуации.
Safety. Yeah. 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 Okay.
So this is lithium ion battery,
Yeah.
which the basic principle for all battery,
Yeah.
or when we enter battery, when we study battery. So this is reflected how many layers.
Oh, no, it's not graphite. So very thick graphite. Yeah. That time people didn't know about graphite. It's a thick graphite. You can. That's the thing. Graphite is so cheap. You can dig it from the ground. That's what you have in your pencil, right? Your pencil you have graphite. Very cheap. Okay, so this is actually the graphite, how it works. So if you look at graphite or lithium, you know the graphene sheet is hexagonal structure, right? So typically lithium ion goes every other hexagon. Like that's why we have lithium 1C6. For 6 carbon atoms, you take 6 carbon atoms, you get only 1 lithium ion. So that will limit your capacity. So that's why we have only 372. So, but if you want higher capacity, you should be able to put more lithium onto this network. That's what we did recently. By making graphene spheres, we could make more lithium onto this carbon network. I'll show you that. Okay. So this is what we have right now with the standard lithium-ion batteries, what we use. So now, but there are some other materials. So this is carbon. So you have 372, right, capacity. But look at tin. Tin has more than 1000 milliampere hour per gram. If you take silicon, silicon has almost 4000 milliampere hour per gram. So then why don't we use these two instead of carbon? So that's natural, right? Because this is almost more than 3 times larger. This is more than 10 times larger. So still we use carbon. So why don't you use tin and silicon? The problem is this expansion. So if you integrate lithium into silicon, it expands more than 40% actually. So in this case it's about 300% expansion. So if you put it inside, it becomes big. So then it explodes. So next time, lithium cannot go in. So graphite is nice, right? Because these are nice. So they go in and they come out still fine. But lithium, for silicon or tin, when you grow in, this becomes big. So then it explodes. So that's why we cannot use silicon and tin. But we found a way to avoid that expansion by making nano materials. So that's what I'm going to talk next. Okay. So actually I can show you some, this one shows what happened. This is actually some in situ experiment people did. Look at, this is a silicon nanoparticle. So now lithium is coming in. So you can see now lithium is coming in. This is expanding. So then see, just breaking apart. This is a very nice experiment. This is done inside the transmission electron microscope. See, lithium is coming in, when it is expanding, then eventually it just explodes. That's why we cannot use silicon in this form. You can see nicely, right? But graphite, if you do this one, nothing happens. It's very small experiment. But silicon, that's a big problem. That's why we are trying to use, is that, okay. Nanostructured electrodes. This is what we are doing in our lab. So we make mostly silicon and tin nanowires. Why are they useful? Because they have very large surface area, nanomaterial. So then also it has enough larger space for lithium ion to go in. So then they have large surface contact area for lithium, and also the diffusion lengths are short. That means because if I have something like that, so lithium can lithium electrons, right? When lithium comes here, so they give electrons or take electrons from this one. So electron can transport very easily along the nanowire. So because your diffusion lengths are much shorter. So it goes other way. So then same thing. Both electrodes have to be nanostructured. Okay, so these are some of the advantages having mostly nanowires, but there are some other problems associated with that because making nanowires are costly. Because, like graphite, for example, if you take abundant, it's freely available, it's very cheap. But if you make nanostructures, cost is very high. Then also it has, since surface area is large, it can discharge very easily too. That's some of the disadvantages. So that's why a lot of research going on this nanowire geometries. So this shows some of the things that I was talking about. Ongoing path and wavelength changes. It's not only for batteries, for any energy application, these are important factors. This basically justify why we want to use nanowires. So this is one example what we did. So actually we have a patent on this discovery. So you can see like if I use tin dioxide nanowires here. So this is a very nice nanowire, very high crystalline. But if I use lithium, so still eventually it is going to dissipate. So what we did was, in the nanowire, because it's some thin metal clusters, so small clusters, but the important thing is the separation between these clusters have to be larger than this diameter. So that means what whole idea is when lithium goes in, so they are trying to expand, right? That's like 300% expansion. But when you have these metal clusters, they take some of that expansion stress. So that way we can keep the nanowire intact. They don't collapse, nanowire. So because of the nano clusters, so when they take the stress, we can retain the nanowire intact. So important thing is to have this enough separation because they should not combine together. If I have them too close, what happens? They are too close. So then when they expand, they become one cluster. Right? So then again it's like a thin film. So it doesn't help. We need to make sure they are well separated so that they don't merge together. So when we did this one, TEM images. So this is the nanowire and these are how the clusters are deposited. So this curve shows you how that works. So this is the capacity, this is number of cycles. So if I use just nanowire, so this first curve is given the circles here, just the nanowires without these metal clusters. You can see after, initially we have very high, like 1600, after first cycle, it goes down to almost 400 and eventually it becomes so small. So that means your structure is going to disintegrate. So it's not good, right? So it's going to be very low. First what we did was, we just mixed metal thin powder with these nanowires. The second one, the triangle. So we just took nanowires, then mechanically mixed with metallic thin. So it did better than this one, but still it is going down. But when we deposit these thin nanoclusters, we did this one, which is a plasma technique. So now your capacity stays pretty stable. So actually we did even for like 100 cycles. You can see your capacity stays almost 1000. Also it has what is called the Coulombic efficiency. So Coulombic efficiency means how much you can extract after you put it in. So that means if I put like 100 charges in, I should be able to take out 100, right? So that means 100%. So this is, your Coulombic efficiency is almost 99%. So this is, that means everything you incorporate, you can take it out. So that means this one was very good. Using these thin nanoclusters covered in nanowires. Yeah. Yeah.
Now we use nanowires.
Still not commercially, no. It's too expensive still. So this only works in the lab, not commercially. Yeah. Yeah, that's. No, this graph is only for that one. Yeah. The first graph, you have 3 different samples. Yeah.
Мы используем нанотруд. Очень хорошо. Вы видите, здесь разрешение на 5 миллиметров, то есть они буквально несколько сантиметров. Если вы беспорядочно, у них у нас они абсолютно беспорядочно будут сочетаться, в эти кластеры будут струнно соединяться, и у нас, пусть вначале у нас будет хорошая емкость, но с несколькими использованиями она уже упадет до минимума. И коэффициент, сколько мы можем оттуда взять из помещения, то есть сколько помещаем, сколько достаем. Здесь у нас чуть не до 60% приходит, если это все беспорядочно. Какие способы обработки мы используем? Мы берем наше олово и помещаем в виде кластеров на года. Очень важно, чтобы расстояние между кластерами было больше 37 диаметра кластера. Тогда они, как показано на доске Гамини, не соединяются друг с другом, а когда на них осуществляются ионы, они остаются отдельно друг от друга, что нам позволяет избежать вот такого гранита. Вот, собственно, в фотографии на 10 нанометрах мы видим этот кластер, он абсолютно крушение. Гамини использовал 2 способа обработки. Когда они просто смешивали эти трубки механически с пылью, маловерной, очень мелкими частицами, у нас получился вот такой график. И, как мы видим, 99% того, что мы туда помещаем, мы можем достать обратно. Даже почти 100. И второе, так как когда мы обрабатываем с помощью плазмы, то есть кислота плюс с помощью плазмы. У нас, видите, очень большая емкость. Он сравнивает график по
we did the same thing for silicon nanowires also. So you can see this one. So silicon nanowires. So when we after lithium integration, you can see still nanowires are there. Yeah, just some new experiments on the other. But we can see after lithium integration, still nanowires are not falling apart. So then the recent results we are doing is actually very exciting. We managed to make graphene spheres. So you can see these are graphene spheres. So this is individual. So each sphere is just single or maybe two layers of graphene. So when you have this one, this is still carbon, right? Remember graphite, you can have only one carbon, one lithium for 6 carbon, right? So this gives you 372 milliampere hours per gram. But when we use this graphene, we see our capacity more than 1000. That is, so also it shows, actually this sample is still going on. This is probably people who are working on electrochemistry, you know, these are very slow. It takes 1 month to, more than a month to finish this experiment. Because it's a battery recycler, goes very slowly. So when I was coming, it was, I think, finishing like 80th cycle or something. Hopefully it will go for a long time. So you can see charging, discharging, very good coulombic efficiency. Maybe this one has more than 90% discharge. So how is it possible to get this 1000 instead of 372? So typically you should have one lithium for 6 carbon atoms, but this is again carbon, but this shows more than 1000. So then also we need some rate capability. Remember, you can make this one charge at different rates, right? So if I apply high current, it will charge very fast. If I apply smaller current, it will charge slowly. So then what we did was here, you can see initially we discharge or charge with 100 milliamperes hour per gram. Sorry, 100 milliampere per gram. Then when I increase my current, it slightly go down. Then I increase it to 500. So then when I go to 5 amperes per gram, it becomes slow. So then when I decrease again, it gets back to your initial value. This tells you good cyclicity. So if it's a bad battery, when you come here, when you decrease, it will never go down. So this is how you test your cyclicity. You have to change, we call the C rate. So C1 means you discharge your capacity within 1 hour. So C2 means you discharge in half an hour. C2 means you discharge in 2 hours. So that's how your C rate is given. So in this case you can see it's very nicely charging, but the important thing is why it is more than this 1000. So then we checked with some theories. So actually they have the mechanism why it is like this. Because typically, like I said, you have carbon atom for every other hexagon, right? So remember, previously we had draw these hexagons. So you have every other hexagon has lithium ion. So but when you have these graphene spheres, you can have actually these lithium clusters. So in addition to this every other hexagon, you can have lithium cluster. So this one has like 2 lithium atom cluster. So that will increase your capacity, right? So then also recently there was some simulation. They think you can have even higher degree of clusters, not just 2 lithium. So you can have 3, 4 and like that. So that means there's no limitation. You can have any large capacity depending on how the lithium can be incorporated into this graphene surface. So this is really interesting stuff. So you can actually explain this like typically when you have some lithium atoms decorated, the barrier, we call the Gibbs barrier, actually that's going to decrease. Otherwise what happens? Then it will put more and more lithium, then you will basically plate your graphite. So it's more like we call it lithium plating. But if this one decreasing, that means when you have more lithium atoms, the barrier decrease means you don't really plate it. So then you have this number of graphene, but this is most electrochemical potential gradually increases. That gives you higher capacity. This is the theoretical explanations, but we have to do some more work. This may be a little too complicated. Yeah.
Can you explain the third graph, please? What's the purple, red, and yellow stands for?
Oh, so here, so the color tells you whether it's close or far away from the graphene. So yeah, in this case, this n equals 3, so the red one is away from the graphene. Like if you have like this, suppose this is your graphene, we have 3 like this, so the red one is the one away from the graphene. Other 2 are closer to the, so these 2 are closer to the graphene, this is away from the graphene. So this is also like these 4 are not in the same plane, it's in the different planes.
So this is formation of ions.
Lithium atoms actually. These are clusters. Lithium 3 atom cluster. This is 2 atom cluster. So this is 3 atom cluster, 4 atom, 5 atom.
0 points now the farthest from the...
Yeah. So this is the ongoing investigation. So this is why you can not 372. You can actually. This number is very interesting. What we get is almost 3 times of this one, right? Very close to 3 times. That means we are getting Li 3 Cs. This is what we are getting instead of Li CCs. This is the one 372. We are getting almost 3 lithium atoms for 6 carbon. So this actually kind of changes people's understanding or thinking. Is that okay? Okay, let me quickly get everything. So then there are some lithium-ion battery safety. Everybody remember this one, Sony battery catching fire in a conference. And recently there was a fire in some Boeing airplane. That's lithium-ion battery. It's all because of this thermal runaway. Because they have some exothermic reactions happening in the electrolyte. Then also, remember we have metal oxide. Right? So that evolves oxygen. So when you have exothermic reaction in the presence of oxygen, so you're asking for trouble. So then also some short circuit. If you have some metals, like we have lithium, and if you have some copper, aluminum, typically your electrodes are, you have copper collector, then you have aluminum collector, so then you have lithium deposit here. All these metals can make it short circuit. So that can cause some of the safety issues. Okay, let me quickly go over to, so now when you look at these batteries, so previous slide I showed up to here, right? Lithium, remember? So I showed you this is the good one for lithium ion, but right now lithium ion batteries are here, but eventually we need to get somewhere. If you want to go for electric vehicles, you need to get at least here. But people believe this is the limit for lithium ion batteries. Whatever you do, you cannot go beyond here. But there are other battery chemistries, especially lithium sulfur and lithium air batteries. They have much higher capacities, but still it's not in commercial stage. So they are still in R&D stage. But they have much better potential for battery application. Lithium sulfur and lithium air. So I'm going to talk a little bit about lithium sulfur batteries. Beyond lithium ion. Because lithium ion cannot go above this one. So here maybe you might get somewhere here, but nothing above here. So you have to go in the lithium sulfur and lithium air batteries.
What's your big batteries? What do you think you think?
Oh, the day is still big. Even that one will be here. So one thing we have to understand is these are two series capacitors. Right? You have one for anode, one for cathode. So then your real capacity comes from these two series capacitors. Right? So your anode and cathode. So typically we measure everything in half cell, like with respect to lithium. So when you put together, your total capacity is coming from this one. So that means it's limited by your smaller capacities. So that's why you cannot make it where you go. That's why we have to go for these technologies beyond lithium ion. So lithium air that can have much higher capacity. This is like 1 hour per kilogram. Actually, one thing maybe students should know. So typical battery capacity is milliampere hour per gram, right? So but you have say voltage. If I multiply this one by your voltage, you get watt hour per kilogram. You can work out the math because this is 10 to the power minus 3, this is 10 to the power minus 3, so this works out exactly same. Watt hour per kilogram, that number multiplied by V is watt hour per kilogram. So I'm going to talk a little bit about lithium sulfur battery. So why lithium sulfur battery is interesting? All the cathodes, so they have very low capacities. So look at all the cathode materials. These are all the cathode materials people use right now. So you can see all they have capacities less than 400. So the anode materials, they have higher capacities, like if you go to lithium or silicon, they have about 4,000. So another important thing is the voltage. So what you need is, so this is like mu anode, so cathode. So this is your mu anode. So this is the same voltage, a difference. So if this is higher, that's good. So this should be smaller, right? So that means you have a higher potential and this one should have lower potential. That's why graphite is good, that has only less than 1. So this one has about 4 volts. That means your same voltage is about 4 minus this value, right? So but the capacities are less than 200. These are all the cathode materials. So but yeah.
то, что совсем исследовано. Он говорит о том, что какие у нас потенциалы и емкости есть у которых то есть видите, это у нас виды, содержащие катоды. Как вы видите, у них около 4 год и достаточно небольшая емкость, около 400. Если мы говорим о литии, то здесь и кремний, то у них огромные, конечно, емкости, но они достаточно маленькие потенциалы. Из чего нам интересен именно графит, потому что они примерно одинаковые емкость и очень отличается потенциал. За счет этого можно добиться хорошей емкости.
So what if you look at sulfur? Sulfur has about 1700 capacity. So you can use sulfur as your cathode, then you can get much higher capacity. But what's the problem with sulfur? It's an insulator. There's no electrical conductivity. Sulfur is a big insulator. So that's why we have to do something with sulfur. So best thing to do is mix with carbon. So that's what we are doing. So we just actually mix with graphene. So then how does this lithium sulfur battery works? So you have lithium as your anode. So then sulfur as your cathode. But we usually sulfur we mix with some kind of carbon to increase its conductivity. Otherwise you cannot do it, right? So you need to have electrical conductivity along with the sulfur. So typically this is the discharge or this is the charging. So charging, what happens is sulfur is a ring structure, right? It has sulfur A. So during charging it goes through this. Finally it becomes Li2S or Li2S2, but it doesn't directly go from here to here. It goes through this intermediate we call the polysulfide. It makes Li2S8, Li2S6, Li2S4, then eventually makes the final Li2S. So if you take Li2S, so it gives you voltage 2, the capacity is about 1670. Problem is these polysulfides, they dissolve in the electrolyte. So these are stable, that's the final product, Li2S. But the polysulfides, they dissolve in electrolytes. So that means you cannot recycle them. That's a big problem. So polysulfide dissolution is the biggest problem. Because when you charge, again, when you discharge, it goes from Li from here to this one, then again becomes SA. So then it becomes what's called polysulfide shuttling. That's the problem is dissolution of this intermediate polysulfide. So how do you avoid this one? What we try to do is wrap this sulfur with graphene. So if I have sulfur, if I can wrap with graphene, so then this polysulfide cannot come out, it can be contained. So that's something we have been successful. Because still electrolyte can reach this one, but polysulfides cannot come out. That's what our strategy. Yeah. Okay, yeah. So this is this one explains what I said. So this is charging. Charging go from Li2S to SA, discharge Li2S to this one, but before it makes Li2S, it will dissolve into the electrolyte. That's the problem. So another problem is if you use anode as lithium. So lithium can make some kind of we call it dendrites. So lithium metal, it makes something like in the anode side, if I have lithium, they make some kind of dendrite formation. So they can eventually shorten the cell. So that's another problem. So for that part we need those, instead of lithium, we use lithium coated nanowires. We take like silicon nanowires, we coat with lithium. So that seems to work pretty good. So this is some of the results we have. So you can see, so this is charging and discharging. So initially we had about 1600. So even actually, so this is, I think this is like after 10 cycles or something. Still it is fading but very slowly. So initially when we did this one, first cycle had 1600, after second cycle it's almost here. But now we are making some progress. So you can see still it is fading after 20 cycles. So still staying around maybe 700 or something. Still we have to do a lot of work. But I think we are making some progress. Okay, thank you. I just want to now a little bit about the supercapacitors. So supercapacitors are maybe about 4 slides or minutes or whatever. Supercapacitors are high power devices. Right? So batteries are high energy. High energy means how much charge you can store. Capacity is how fast you can charge and discharge. So high power density, supercapacitors, batteries are high energy density. So everybody knows the capacitors. So typically if you have 2 plates, if you charge them positive and negative, so we know we have electric field, right? So then you have potential. If you increase the charge, your potential is going to increase. So then we know the potential is proportional to the charge. So then we have this constant capacitance. So capacitance typically defined by this equation. Dielectric constant, what you feel here. Then this is the relative dielectric constant. Area and the distance. So if you want large C, you have to increase area, right? Then you have to decrease separation. But how much can you decrease here? Physically you cannot, right? So that's why it comes to this what is called the supercapacitors. So if you, this is the one I was talking about now. So if you have just 2 plates with the dielectric here, you can see your electric potential is linear. That means your electric field is constant, right? But that's what is called the electrolytic capacitor. That means you have electrolyte here, liquid. So then you can get this interface here. You get some sharp drop in your potential that increases your capacitance. But if you go to electrochemical capacitors, there are 2 kinds of capacitors. One is what is called the double layer capacitors, EDLS, C. The double layer electric double layer capacitors. Electric double layer capacitors. That means you have actually 2 layers. This is your electrode. There's other electrodes. At the interface, you have this ions from the electrolyte and the ions from the electrodes. If you take like this, you have this positive and electrolyte, you have negative, like this. This separation between these charges are nanometers, right? Even angstrom. So that means your D is very small. If you take a epsilon over D, when this is small, your C is going to be huge. So that's why you get this double layer capacitor, because you have 2 of them, right? 1 electrode. So we call the Helmholtz layers here. So that will give you this large capacitance here. So then again we have, so again at this interface we have this. So then also there's some what is called the pseudo capacitance. That is when you have some kind of redox, like charge transfer between electrode and the electrolyte, then you get additional capacitance coming from the what is called the pseudo capacitance. Whenever you have any charge transfer or electrochemical redox reaction, you have that additional pseudo capacitance. So you need to have very large area surface and this double layer almost double layers. That's the electrochemical capacitance. Oh. That's a voltage. Voltage versus distance.
Если взять обычный периодический конденсатор, то у нас здесь есть неделя, собственно, между двумя электродами, а кивание движения в зависимости от расстояния от одного электрона до другого идут линии. Если мы возьмем здесь оксид, слой оксида, тоже диэлектрика, а здесь у нас будет электролит, то у нас будет кривая совершенно другая, у нас будет очень большой скачок напряжения. Возьмем наши суперконденсаторы. Они бывают такие двухслойные,
Pseudo really means not real.
Псевдо. Здесь у нас идет два слоя вещества, и кривая у нас имеет такой же белословитель массы. Она очень резко. Дальше идет линейно, как следующий определитель, но снова резко. То есть очень большое напряжение можно достичь этого меня плавно. И так.
Yeah. Yeah, so that's mostly if you have, this is all electrostatic, so just charges, but here you have some electrochemical charge, yeah, reaction. Yeah. So let me quickly go what we need to. So this is some of the applications of supercapacitors. Actually, people use it very much in these the UPS systems for the power. Most of these large instruments we usually use UPS. Right? When you have power failure, you can use for fast charging of your system. So then also people use for even in some airplanes, so even some brake systems, and so a lot of applications in this hybrid electric vehicles. So the supercapacitors are used everywhere now. Whenever you have high power need, you have to use a supercapacitor. Okay, so this is what my research at Louisville. So like I said, we have these dried distilleries grains from the distilleries. This is what we receive. So then there's a group working on this the biofuel. So what they do is they pre-treat and do this selective hydrolysis, and eventually they make biofuels. So I'm not involved in this project because it's not my area. So they give me this rejected waste. Once they do this one, so I get this even the more waste from this one. I usually actually not even here. So this is the product they give to me. So then I carbonize it and activate it to make activated carbon fibers. So this is very simple one. So what I do is I put it in the furnace and heat it under flow with nitrogen. So then activate with potassium hydroxide or some other elements. So that way I can make very high surface area carbon fibers. So we can make from this material, we have already made active carbon fibers that has 2000 meters squared per gram. That's very huge surface area. Because they have a lot of this micropores and mesopores that will have very large surface area. This is a huge surface, this almost size of a football field in physical dimensions. So 1 gram will have over 2000 square meters. So these some of the features of the the carbon fibers. If you look at this one, they have these small pores, micropores and millipores. So that's why they give very large. So this initially we got about 700 meters square per gram. Then we, by changing the parameters, now we are getting close to 2000 meters square per gram. So then when we look at the charge capacities, so this is how we calculate the capacity in typical electrostatic capacitors. What are the capacitors? Typically either microfarads or nanofarads, small capacitors, right? But with these things you can get farads, even kilofarads. So that's why these are really interesting. So by this term I can calculate my specific capacity. How do we calculate that? Simply, if I have suppose ideally it should have this kind of curve, charge and discharge, triangular, right? So if I take this voltage V1 and V2, I can easily calculate my capacity. C is given as Q over V. So this is typically Q is, we know the current times your time. So delta T divided by your voltage is V1 minus V2. So if you divide by M, you get farads per gram. So in these samples, we get, so the highest one, so this is for 700, this is for 1300, this is for 1900. So this one gives, I didn't have the capacity values, this one gets almost like 200 farads per gram. That's still not that great, but still pretty high. We can definitely improve this. For those who look in chemistry, actually mostly chemists do this one by doing the CV. So ideal supercapacitor should have your capacity like rectangle, but usually you see something like this kind of behavior. So by taking this area, you can calculate the same capacity. So for that you need to calculate your area here. So then your capacity is given as the area divided by your this voltage window V2 minus V1 times your average current. From here you can calculate. So you can do galvanostatic or CV. Either way you can do capacity. Okay. Yeah.
With the fibers.
What's that?
With the fibers. So
Oh, this whole thing is a fiber. Yeah, but the
on the top.
yeah, no, the whole thing, they are long fibers. So we just look at the pore structure. So if you look at here, you can see you have large pores, then smaller pores. So there are three kinds of pores. You have micro, meso, and macro. So 3 different kinds of force, so depending on the size of the structure. Usually they look like long pipe fibers. We just look at it. Yeah, it's all random. Yeah, that's why you get this large surface area. So eventually what you like to make is hybrid battery and supercapacitor. So that's what eventually what we like to do is, because battery has large energy, capacitor has large power. If I can use one electrode from battery electrode and one electrode from capacitor electrode, you can get something big. So we call the hybrid batteries capacitors. Okay, I think that's pretty much, let me show the last slide. So this summarizes everything I told you. So this is storage time versus your power. So you can see supercapacitors, they have enough power, but storage time is very short. If you go to hydro, it takes several hours to store your, so what your energy power is very high. So this tells you the storage time, and this is the power. So lithium ion has, still you need about 100 minutes to charge, right? But if you can bring it down and has something higher power, that would be nice. This gives you some idea where your pump hydro, and that's why a lot of people are talking about these flow batteries. They have very high energy and power densities. That's something another interest. They are more like fuel cells, but they have different redox frequencies. Okay, so I think that time is too long. Almost 2 hours. Yeah, please, yes, yeah. Any questions? Yeah. So if you, yeah.
How will you improvise the grains in chemical use space or mineral?
Yeah, so actually that's another area of research for the power electronics. So that's what actually we have a new person recently joined our center, so he's going to work on that. So it's mostly switches. So how you change your storage system very fast switching. So they have inverters, converters, so it's all power electronics. So fast switching. That's the power electronics. Before one from the, this is how it works. If you go from storage to grid, you need to have, this is called the power electronics. This is where everything happens. So this DC to DC, or DC to AC, and all this. It's very fast switching. That you cannot use with silicon. Your silicon, you cannot take very high voltages. You cannot have fast switching. For that, power electronics requires wide band gap materials like gallium nitride, silicon carbide, this kind of semiconductors. Power electronics is a completely new area. So we have person now. Actually, we are trying to hire somebody. I'm the chair for the search committee. There's some expert here, so we can hire somebody for this power electronics. Mostly electrical engineer. Sorry, it's too long. Selenium.
Not sulfur, but selenium.
Selenium was actually, earlier people is too toxic. Yeah, so because of the toxicity, people don't like it. Yeah, that's why. Otherwise, even for like these solar cells, we have the what is called using gallium, indium, tin, sulfur or selenium. So actually selenium gives better efficiency because of the toxicity people still go for sulfur. Yeah, selenium works better actually. So there are a lot of these restrictions using selenium and things like that. Yeah. So this is the seeds, right? Copper, indium, gallium, sulfur or selenium, they both work. Yeah, selenium should work at least. So there are two things people like to have earth abundant material. So if something you can, because sulfur is very earth abundant, you can find it very easily. Other thing is the toxicity. Otherwise sulfur and selenium same chemistry. Yeah.
So we were talking about this atomic batteries,
Yeah.
these supercaps and
Yes.
what's their application? Is the question on the size?
No, always capacity will be lower and energy also going to be lower, but it has both advantages. Yes, balance, exactly.
What's the application of that?
Oh, there's a lot of even if you look at not the electric vehicles, even things like hybrid cars. So that has both, right? You have the acceleration and the distance. Those kinds of things. But overall value will be less each one.
Professor Ghamini,
Yeah.
as I am not physics and only chemistry, but
Yeah.
I spoke about this compound, benzene.
Yes.
What it is used for?
Yeah, that's because that's something that's a good question. Yeah. Yeah. So when we were trying to make this sulfur, so initially what we did was we used sulfur powder and just wrapped it. So that doesn't work. So then we found this metal and two sulfur metals. So they gave some, actually initially they used some one sulfur. So then my student, he found if you use two sulfur, you can get better capacity. So actually what happens is, so one metal gets displaced and this gets attached to the graphene surface. So he tried different like dye, then try sulfur. Okay, thank you for your attention. Tomorrow's talk I'll make shorter.
Завтра 902. После завтра снова из нас.
Oh, okay.